What can we learn from analyzing the physics of collisions? What factors are important for understanding the severity of a collision? We will find answers to these and other questions in designing and testing crash cushions. Sometimes automobile accidents are unavoidable. In many cases, a car that loses control might come to a stop harmlessly in a farmer's field. However, if it collides with a steel bridge column or concrete barrier, the chances for harm increase dramatically. How can we protect the occupants of a car in such a collision? What factors are important for the design of one solution to this problem, crash cushions? We have attached a wireless acceleration altimeter to this cart. It will measure the acceleration as a function of time when it collides with our crash cushion at the end of the track. The other end of the track is elevated about 10 centimeters. It's really sturdily connected to the table so the track doesn't move when it collides. The track is a scale, so we can make sure the cart has traveled the same distance for every collision. This ensures it has the same initial velocity at the start of each collision. We'll need the mass of the cart and the acceleration sensor later. Let's measure it before we forget. So it's 300 grams or 0.3 kilograms for both together. We've created an acceleration versus time graph display on SparkView. Since the collisions happen over a short amount of time, we've increased the data sample rate to 250 hertz. You might even turn yours up higher if you're doing this, if your computer can keep up with it. First, we'll measure the acceleration of a collision between the cart and just the end stop. This simulates a collision with a rigid object that doesn't have a crash cushion. We can compare this data with our crash cushion data to see how well they work at reducing the acceleration. After I start recording data, I'm going to release the cart from rest 60 centimeters from where the collision occurs here at the end stop. So that's at 110. And so if I release it from 50, then it'll have traveled 60 centimeters down. Let's take a look at the acceleration versus time graph. The big spike is the collision. Let's zoom in on that. I have the selection tool, and so I can just drag it over that. I don't want this other spike. That's when it bounced and hit again. Then I hit the auto scale, and then we can get a really good look at the acceleration during the collision. It's negative because the positive direction for the sensor, the way I attached it, is down the track. And so since it's slowing down while moving in the positive direction, that is negative acceleration. We need to find the largest negative acceleration with the coordinate tool and record its magnitude. In other words, we can ignore the minus sign in the data table. And so the coordinate tool is there. Drag it to where I see the largest. And so it says negative 138.6 meters per second. So I record 138.6 in the data table. The crash duration, well, I can see when it started, when the acceleration zoomed up from essentially 0, and then when it went back to 0. So either here or here. I think that's the better place. And so the coordinate tool has a delta function, this little delta. And so if I click on that, I get another point, and it tells me the difference between those in the x and the y direction. Well, the x direction is time, so that's 0.025 seconds. So I'd write that down in the data table for the crash duration. We're going to repeat the collision for this ring-shaped crash cushion. And so it's following the guidelines in the lab. It's less than 10 centimeter diameter, less than 5 centimeter height. And I put that in front of the end stop. But now I don't want to release it from the same place because it's closer to the crash cushion. So I need to back it off about another 9 centimeters or so. And so again, using the scale on the track, I can make sure every collision happens after it's rolled 60 centimeters down the track. So here we go. So notice the presence of the crash cushion. If I show the first collision here, reduce the peak a little bit, but maybe we can do better. So you'll need to record the maximum magnitude of that acceleration and the crash duration in the data table. I showed you how to do it. You'll be doing it for yourself from now on. Now let's collide with the same ring crash cushion a second time. And so after a collision, it's better to replace the crash cushion. But you don't always have a chance to do that. And so a crash cushion that could work for 2 collisions would be very useful. The lab handout asks you to predict what will happen to the peak acceleration and crash duration for the second collision. Will it work as well, better, or worse? Make your prediction before you look at the data. Again, we want to back it off 60. There we go. Could you design a crash cushion that performs even better than the ring? Now we will design and test our own crash cushion. We want to have a lower peak acceleration in its second collision than the ring cushion had for its first collision. If you're designing your own, it may help to research crash cushions. There are many different designs that you can read about online and some really good videos of actual tests with cars. You'll test your design and try to improve it over 5 trials. Remember, only include data from the second time the cart collides with your crash cushion in the data table. If you're unable to test your own design, keep watching and you can see how mine performs. If you are making your own, remember you can use cardstock. Here I have file folders, tape, and scissors only. So I've made another ring cushion, but added a smaller ring inside. I got this idea from watching crash cushion tests and noticing them on the highway. I often see a row of barrels used as crash cushions. Breaking the collision into a series of smaller ones can extend the duration and maybe lower the peak acceleration. By nesting them, I can ensure they don't move out of the way during the collision like barrels might. Here we go. For my next trial, we got to do 2. So remember, don't forget. So you can see the first collision here and the second collision there. For my next trial, I did something similar, but I made the inner ring smaller. See what that effect is. I'm always putting them like this on the track. So again, release it so it goes 60 centimeters. And so again, there's the first collision, there's the second one. So the second one is all you're going to worry about. Then I decided to just keep adding more rings. So this one has 3 rings. Then I'll do 4 rings. And finally, 5 rings. Maybe it'll keep improving the crash cushion. Maybe it'll stop improving at some point. It'll be your job to find that out using this data file and the lab handout. Remember, measure the peak acceleration and crash duration only of the second collision on each graph. So again, here we go. Start recording. 1 collision. Second collision. And then now 4. One collision. Second collision. And And finally, 5. That is a work of art. It's a shame to wreck it. No. So now we have all the data for you to figure out which one worked the best, and hopefully you'll someday get to try your own ideas out. Engineering something like a crash cushion requires teamwork. Although you may not have been able to design and test your own, your analysis of this data will be important for finding out what worked the best. Thanks for being part of my engineering team. We might just save some lives with improved crash cushions that can work for multiple collisions.